Hello, my name is David Morrisset. I'm a PhD student at the University of Edinburgh, and today I would like to share some of our ongoing research looking at flame spread over solid fuels. Now, flame spread is a subject that has received a lot of attention in the history of fire safety science, but it's also a subject that continues to be relevant today. Now, the rate at which flame spreads over solid fuel dictates fire growth, and therefore flame spread itself governs the relative fire hazard across many scenarios in both the built and natural environments. So characterizing the rate of flame spread has been a subject of research for decades, right? But there remain some fundamental questions that have yet to be answered in this field of flame spread. Some of these questions include, what is the relative magnitude of gas phase versus solid phase heat transfer across a range of flame spread scenarios? And then how do these relative magnitudes of gas phase or solid phase heat transfer then play a role on the overall flame spread rate? So this video outlines some of our ongoing research, particularly aimed at answering some of these questions. So let's start with the question, what is flame spread? Now, the rate at which you get flame spreading over a solid fuel is generally broken into two categories. One being concurrent spread, or spread in the direction of ambient flow over the fuel surface, and opposed flow flame spread, or spread in the opposite direction of ambient flow. Now, each of these categories of spread have their own significance in understanding fire dynamics, and both are integrated into the regulatory testing system for material flammability. Now, in this study, we'll be focusing on opposed flow flame spread in an effort to study a steady state process in which we can interrogate the relevant physics with a high degree of fidelity. As I mentioned before, there's a wealth of existing literature on flame spread. These studies represent some examples of landmark publications in developing the framework for which we currently use to describe the flame spread problem. These works employed both experimental and analytical approaches to understanding the processes that dictate flame spread. Please see our corresponding paper for further examples. One study I'd like to highlight is that of Ito and Kashiwagi from 1988. Their study showcased data quantifying the thermal gradients in the solid ahead of the flame front. Now, knowing these thermal gradients in turn allowed them to approximate the heat transfer from the flame to the solid ahead of the flame front. In other words, taking these measurements allowed them to quantify the relative magnitude of heat transfer through both the solid and through the gas phase. Our current study very closely emulates the goals of Ito and Kashiwagi. As such, this work is largely inspired by their study, namely in quantifying these thermal gradients ahead of the solid and the resulting heat fluxes from both the solid and gas phase. The experiments I'll be presenting today focus on opposed flow flame spread over polymer fuels, looking at how different experimental configurations influence the controlling mechanisms, or in other words, the key heat transfer contributions that govern the flame spread process. Now, before we dive into the experiments, let's frame the problem a little bit more. Let's start by focusing on downward spread over solid fuels to contextualize the flame spread problem. What we see here is we see the leading edge slowly working its way down the fuel. And if we take a side view looking at this, what we'll see is a boundary layer type flow attached to the solid. Now let's just focus on the region within the solid at the leading edge and take a closer look. Here you can see a cross section of the solid with the flame anchored above the surface. The flame is spreading at the rate of V sub F along the surface, while the entrained air flowing at the surface moves at U infinity in the opposite direction of flame spread. The region beneath the flame is undergoing pyrolysis, and there exist 2D thermal gradients that extend ahead of the flame front. From this frame of reference, we can establish our preheated distance along the surface, del, and the thermal penetration depth, tau. Heat transfer ahead of the flame is broken into two categories: gas phase heat transfer from the flame to the solid, and conductive heat transfer through the solid ahead of the flame front. Gas phase heat transfer is achieved through both radiation and through gas phase conduction across the standoff distance. In some opposed flow scenarios, such as downward flame spread, it is often assumed that radiation is negligible ahead of the flame front. Now, this is due to the nature of the blue leading edge as seen here. In such cases, gas phase conduction is generally assumed to be the dominant heat transfer mechanism for gas phase heat transfer. However, assuming radiation is negligible may be inappropriate for other conditions such as horizontal or lateral spread, as we will see later on. Solid phase heat transfer is driven by conduction from heated solid beneath the flame to solid ahead of the flame front. If one is able to resolve the temperature distribution through the solid ahead of the flame front, then you can approximate both your gas phase heat transfer and solid phase heat transfer terms. This is achieved through evaluating the heat fluxes both along the surface and in depth at the flame front. For example, Q sub x, or our solid phase heat transfer term, is defined as the conductive heat flux across this boundary seen here and is calculated in this form. This effectively evaluates the temperature gradient at the boundary beneath the flame front. Similarly, Qy, or our gas phase heat transfer term, can be found by evaluating the thermal gradient along the surface of the solid. Now, calculating in this way gives you the net heat flux conducted into the solid at the surface. But evaluating this thermal gradient alone does not directly give you the heat flux exposure from the flame. Instead, this is the net heat flux absorbed. In order to calculate the value of Qy, one must also consider other effects such as radiative losses at the surface. These calculation methods effectively take the measured thermal distribution through the solid, as seen in previous work by Ito and Kashiwagi, and allow you to approximate both gas phase and solid phase heat transfer contributions to the process of flame spread. So that's the theoretical framework that we will employ in this study, and then we design our experimental campaign in such a way where we can capture the measurements required to actually calculate these relative heat flux contributions. Now, the experiments presented here were conducted under a range of different experimental conditions. 3 different sample orientations were used, looking at downward flame spread over a vertical surface, lateral flame spread over a vertical surface, and horizontal spread, similar to a floor type configuration. Now, each of these 3 configurations show a post-flow flame spread, meaning at the leading edge, the flow being entrained along the surface is moving in the opposite direction of flame spread. Yet each of these 3 configurations show distinctly different flame shapes, meaning that the relative contribution between gas and solid phase heat transfer is likely to vary across these 3 different configurations. Experiments were conducted with both cast PMMA and POM. Now, these 2 polymers burn with 2 very different characteristic flames, with the POM showing a virtually non-sooting blue flame, and this allows for comparison of these different flames on the flame spread rate. Each sample was also placed in a water-cooled sample holder, which created an isothermal boundary condition on both the back and sides of the sample. Now, this was found to better promote a uniform flame front and a steady-state flame spread process. In addition to changing the sample orientation and the polymer used, a series of experiments was conducted using a cone heater to apply a range of external heat fluxes at the surface. Now, this allowed us to investigate the influence of preheating on the flame spread process. Experiments were recorded, and the flame front position was determined by isolating blue pixels at the leading edge using video processing techniques, which are detailed in the paper itself. Additionally, thermocouples were placed at various depths and locations along the sample, as seen in the diagram here. Surface thermocouples were used to calculate the flame spread rate between 2 measurement locations, and these flame spread rates were then compared to the video data. Now, calculating heat fluxes from this data requires spatially resolved temperature gradients, as we've discussed previously. The process by which we reconstruct those thermal gradients from in-depth temperature measurements is explained in more detail elsewhere, but in essence, this approach uses time-resolved temperature data and steady-state flame spread rates to reconstruct the thermal gradients ahead of the flame front, thus turning time-resolved data into spatially resolved thermal gradients. This results in a high degree of fidelity while minimizing the intrusive addition of further instrumentation. Now, as we move to the results from this study, let's start by comparing the flame spread rates seen across all the conditions tested. Let's first compare the flame spread rates determined from surface thermocouples, seen as the shaded region here, and the video data shown as the solid lines. Now, this figure compares the spread on PMMA for each of the 3 orientations used, that's downwards, lateral, and horizontal, and shows good agreement between the temperature data and the video measurements. It can be observed from this data that the downward and horizontal steady-state flame spread rates were similar, while for the lateral flame spread condition, this displayed a notably higher steady-state flame spread rate. The experiments conducted with an external heat flux are also shown here, indicating a progressive increase in the steady-state flame spread as the external heat flux increases. The trials heated with an external heat flux resulted in a range of initial surface temperatures prior to the flame arrival. This increase in the surface temperature can be tied to existing flame spread theory. More specifically, the initial surface temperature can be correlated to the enthalpy rise required to bring the solid to the pyrolysis temperature. In other words, higher temperatures at the surface prior to the flame arriving led to faster flame spread rates, as this was less of a temperature rise required to actually spread the flame. The correlation of the initial surface temperature and the flame spread rate can be seen in the figure here, which also corresponds well to results from a previous study by Fernandez-Peyo. In addition to flame spread rates, temperatures were recorded at various depths in the sample and at various locations along the sample. The temperature profiles recorded at each depth and time were found to be consistent between each measurement location and between individual experiments conducted. The figure here illustrates this degree of similarity. Taking this repeatability in combination with the consistency of the steady-state flame spread rate, one is then able to retroactively reconstruct the temperature gradients ahead of the flame front using these temperatures. The results of the temperature reconstruction provide temperature distributions through the solid similar to those seen by Ito and Kashiwagi. This study therefore provides a method by which you can reconstruct the temperature gradients ahead of the flame front using relatively simple measurements. Then from these temperature reconstructions, we can calculate the relative contribution of gas phase and solid phase heat transfer across a range of experimental configurations. Now to demonstrate this method, let's start by looking at downward flame spread. Here we have the reconstructed temperature gradient relative to the flame front position seen here. By evaluating the thermal gradient at this boundary below the flame front, we're able to calculate the solid phase heat flux distribution as a function of depth. Then by evaluating the gradient along the surface ahead of the flame front, and by accounting for both surface losses and external heat fluxes, we can then approximate the distribution of gas phase heat transfer to the surface. Therefore, the reconstructed temperature gradients allow for the approximation of both gas phase and solid phase heat transfer components. Now here we can see the reconstructed temperature profiles for downward, horizontal, and lateral spread over PMMA. We can note some general similarities between each case, but we also note that each case varies particularly in the temperature distributions in depth at the leading edge and along the surface. Comparing the lateral and downward cases in particular, we see slightly deeper thermal penetration depths in the downward case, but a much longer preheated distance along the surface for the lateral case. Looking at each of these distributions in PMMA, for each of these three configurations, the following heat fluxes can then be calculated for both gas phase relative to the surface and solid phase heat transfer in depth. Both the solid phase and gas phase heat fluxes are largely found to be the same between the horizontal and downward case. However, the lateral case displays both a notably higher amount of gas phase heat transfer and a lower solid phase heat transfer rate. This increase in gas phase heat transfer is not necessarily a significant increase in the peak heat flux right at the leading edge, but the sample surface experiences higher heat fluxes at a much further distance along the surface. This is reflected in the surface temperatures as well for the lateral case, showing higher temperatures at the surface 2 to 4 mil from the leading edge compared to the downward case. This same process can be done to examine the thermal gradients ahead of the flame front for those trials exposed to an external heat flux. Here we can see the temperature distributions for downward flame spread over PMMA under different heating conditions. At higher external heat fluxes, the surface temperature ahead of the flame front is higher than at ambient, and there's a notable thermal gradient through the solid ahead of the flame front. When considering the gas phase heat fluxes received at the surface of the solid, this method reasonably reflects the external heat fluxes imposed far from the leading edge. Therefore, if you remove the effects of external heating, you can observe the gas phase heat flux from the flame alone. Now, apart from the trial that was conducted at 7 kilowatts per meter squared, the gas phase heat fluxes display similar behavior between each of the heating conditions. We can also compare the solid phase heat fluxes for each of the heating conditions. Here we see a systematic decrease in the solid phase heat transfer as the external heat flux is increased. The last point of comparison to discuss is the difference observed between PMMA and POM. We noted previously the difference in their flame behavior, and this difference can be used to contextualize the results seen here. The thermal gradients seen for both PMMA and POM show general similarities when considering distances up to about 6 mil from the leading edge. However, if we expand this view a little bit further, we can start to see the differences along the surface between these two cases. In particular, the PMMA case displays higher temperatures along the surface at distances beyond 6 mil compared to the POM case. Now, this is largely due to the difference in the radiation from the luminous flame seen in the case of the PMMA, which is why these temperatures are not seen in the case of the POM flame. The heat fluxes show higher degrees of solid phase and gas phase heat transfer for the POM case. Higher gas phase heat fluxes in particular show good agreement with previous studies between PMMA and POM using other apparatus such as the cone calorimeter. Now that we've gone through all the experimental results, let's take a moment and summarize some of these key findings and contextualize the relative contributions of solid phase and gas phase heat transfer across these experimental configurations. This table summarizes all the key results from each of the configurations tested. We can compare the flame spread rates across each configuration, and we can also compare the preheated distances and thermal penetration depths across the configurations used here. Additionally, we can present the total integrated solid phase and gas phase heat transfer contributions. The calculation of these terms is explained in more detail in the paper, but is effectively a total integration of both the gas phase and solid phase heat transfer distributions. This method has been employed in previous studies to compare the relative contribution between the gas phase and solid phase heat transfer across a range of experimental configurations. Now, there's some interesting trends when comparing the ratio of solid phase to gas phase heat transfer. For the three geometric orientations used, we see that both downward and horizontal show higher proportions of solid phase heat transfer, while the lateral case shows a higher relative contribution from the gas phase. Another interesting observation looking at the heated trials is the systematic decrease in the relative contribution of the solid phase heat transfer with increasing external heat flux exposure. Another important observation for these results is that in no case observed here do either the solid phase or the gas phase components become negligible, meaning that in each case that we see here, these mechanisms become increasingly or decreasingly significant, but in no case can they be completely ignored. Now, the associated paper to this work dives into more details on these results in particular, but this study effectively produces a method by which researchers can quantify the solid phase and gas phase heat transfer contributions looking at the flame spread process using relatively simple measurement techniques. Now, this insight can therefore provide further information to future experimentation, can be used to compare to numerical models of flame spread, and can also be used to inform the development of future regulatory testing procedures around the concept of flame spread. Currently, we are actively expanding on the work that's presented here in this study, and we're trying to expand the measurement techniques that we can use to more accurately characterize the solid phase and gas phase heat transfer contributions in the flame spread process. We're also exploring a range of other experimental configurations to see how those configurations influence the balance of solid phase and gas phase heat transfer. So we hope the methods provided in this work can provide experimentalists with ways to then characterize the solid phase and gas phase heat transfer contributions in flame spread, but we also hope that the results presented here can shed some light on this more general results showing the mechanisms that control the flame spread process. And we thank you for your time, and we look forward to any questions you might have on this work.